Hello, everyone. My name is Ethan Farber. I'm a graduate student at Boston College. And today I want to tell you a little bit about my research on constructing pseudo-Anosovs from expanding interval maps. So let's start off with a few definitions. Today, when I say a uniform lambda expander, what I will mean is given a real number lambda greater than 1, some interval map that is piecewise linear of slope plus or minus lambda. Here is such a map down here. This is actually a special kind of expander. It's what I call a zigzag map. Specifically, it starts at 0, climbs all the way to 1, back down to 0, and keeps doing this for as long as it can. A pseudo-Anosov is a homeomorphism of a compact surface S that comes along with some extra data, a number lambda greater than 1, and 2 singular measured foliations of the surface, such that the pseudo-Anosov shrinks one of them by lambda and stretches the other one by lambda. Okay. So Andre de Carvalho defined a process by which we could take an interval map and try to thicken it into a surface homeomorphism. In general, when you try to do this, you'll obtain a surface with infinitely many punctures. But if by chance you end up with a surface with finitely many punctures, then in fact, the map that you obtain is a pseudo-Anosov. And so we'll say that if you have an interval map that can be thickened to a pseudo-Anosov in this way, that it is of pseudo-Anosov type. And our goal in this project is to characterize zigzag maps of pseudo-Anosov type. I won't get into the details, but here is a picture that hopefully gives you an idea of what it means to thicken a zigzag map. On the left, I've marked out the post-critical points of this zigzag map. And on the right, here's a topological disk that is mapped into itself. And these colored regions are mapped into each other in the same way that these colored dots are mapped into each other. Okay, so this endomorphism of the disk is kind of mimicking the combinatorial action of our zigzag map. Okay, so if we want to characterize the zigzag maps of pseudo-Anosov type, a key observation is the following. If you have a zigzag of pseudo-Anosov type, then x equals 1 is actually a periodic point. And moreover, the orbit of this period is acted on by the map by a very particular type of permutation. I haven't written down a formula, but the important thing is that this permutation is indexed by 2 integers, n and k. And these integers satisfy the property that n-1 and n-k are coprime. And it turns out that a zigzag map having this kind of permutation action on the periodic orbit of x equals 1 is enough to tell you that it's a zigzag map of pseudo-Anosov type. So that brings us to our first classification of these maps. So given a modality M, a number of critical points, we can look at the set of zigzags of pseudo-Anosov type of modality M, and we obtain a map from this set into the rationals in the open unit interval. And what does this map do? It takes a zigzag of pseudo-Anosov type with permutation type nk, and it maps that to the rational number n-k over n-1. And it turns out that this association is a bijection. We could actually say more though. This isn't just a bijection, it carries dynamical significance. One thing we can say is that, well, the entropy of a zigzag map, a lambda zigzag map, is log lambda. So this lambda is really carrying the entropy of our map. And we have numerical evidence to suggest that this bijection, big phi, remembers this topological entropy. So specifically, if you have two zigzag maps of pseudo-Anosov type with then the rational number associated to the first is less than the rational number associated to the second, if and only if the entropy of the first is less than the entropy of the second. Okay. There's another way that we can understand these zigzag maps of pseudo-Anosov type. Given a zigzag map, we can define what I call a Galois lift. What this is a transformation of I cross R to itself, which covers the original interval map. So in the first coordinate, we act by our zigzag map. And in the second coordinate, we almost act by the zigzag map, except that everywhere we replace a lambda with lambda inverse. Now this Galois lift is going to have an omega limit set. And we say that this limit set is rectangular if it is a union of finitely many rectangles. So here's a picture. You can cut this into finitely many rectangles. And in this case, this limit set is the limit set for the Galois lift of our zigzag map from example 1. Okay. And down here is a diagram showing a partition of this limit set into rectangles that demonstrates the dynamics of our Galois lift. And what you might notice is that the dynamics mimics the transformation that thickens our interval map. And this is no coincidence. Okay. This brings us to our second characterization of zigzag maps. So of pseudo-Anosov type. So let's say that you have a lambda zigzag. Then it is of pseudo-Anosov type if and only if the following two conditions hold. Firstly, the limit set of the Galois lift is rectangular. And secondly, the reciprocal of the Artin-Mazur zeta function of f is an integral polynomial that vanishes at lambda. So there are a few things being packaged together here. First of all, for a zigzag map with finite post-critical orbits, the Artin-Mazur zeta function is in general a rational function. And what we're saying here is that it is in fact 1 over a polynomial for a zigzag map of pseudo-Anosov type. And second of all, in general, the zeta function will have a pole at lambda inverse. And what this is saying is that it also has a pole at lambda. We can actually say a little bit more. If you have a pseudo-Anosov, a zigzag of pseudo-Anosov type, then this rectangular limit set of the Galois lift is essentially giving us a model for the pseudo-Anosov that you would obtain from the zigzag map that you started with. Specifically, there's a topological conjugacy from the Galois lift that conjugates the action of the Galois lift to the action of the pseudo-Anosov. So in particular, in this picture down here, we can actually take this figure as demonstrating for us the actual pseudo-Anosov that we would obtain from the zigzag map in question. As a final application, using our association of rational numbers to these zigzag maps of pseudo-Anosov type, we can find infinite families that exhibit interesting behavior. So here's one such family. It consists for every G of a bimodal zigzag of pseudo-Anosov type. And F sub G actually produces for you a pseudo-Anosov on the genus G surface. And moreover, its slope is a Salem number of degree 2G. A Salem number is a number, an algebraic integer with very particular algebraic properties. So this is quite interesting in its own right. And if you study translation surfaces, one thing this immediately tells you is that these surfaces you obtain have algebraically primitive translation structures. But let me stop there. Hopefully this was interesting to you, and I look forward to answering any questions you might have.